Okay, test, test, test. Here we go again. Wonderful. So the next topic is one that I'm actually really looking forward to. It's probably one of the topics that is as old as time itself. And just to introduce you to the title so that to create some excitement among you. Helicopter, Snakes, and Decision Theory, the role of AI in space missions, and the hunt for extraterrestrial life. For this one here, we will have our speaker, Steve Chien, who is joining us virtually, and I'm really excited about this conversation, especially because of his exceptional profile on this topic. Steve is a JPL Fellow, Senior Research Scientist, and Technical Group Supervisor within the field of AI and Mission Planning and Execution section at the Jet Propulsion Laboratory at the California Institute of Technology. Steve, can you hear us?
Yes, I can.
Fantastic. Steve, floor is over to you. Ladies and gentlemen, please welcome Steve.
Thank you. So I think I'll just go ahead and jump right in, and I just want to reinforce what the previous speakers were saying about, it's very important to have all the key stakeholders engaged in the entire process of conceiving of and deploying the artificial intelligence.
I'm Steve Chien, and I'm really excited to be here to talk to you about how artificial intelligence is really critical to the search for extraterrestrial life and some of the interesting new robots that are going to hunt for it, including helicopters, snakes, and how they use decision theory. So if we're to talk about the current explorers that we have hunting for life or signs of life, first, we would think about Mars. And on Mars, we have two rovers, the Mars Science Laboratory rover and the Perseverance rover. And we already have significant artificial intelligence on board these rovers. For example, since the MER rovers and going on to MSL Curiosity and M2020 Perseverance, the Aegis system allows us to do autonomous targeting. And by autonomous targeting, we mean that the scientists can specify certain science criteria, and the rover knows enough to take these wide field of view images and find the right targets that satisfy these criteria, and then fire this ChemCam laser on MSL or the SuperCam laser on the Mars 2020 Perseverance rover. And that allows us to burn underneath the surface weathering and the iron oxide dust that you see everywhere to get spectral measurements of the interiors of rocks that tells us about their composition. And so this is a tremendous win using artificial intelligence to extend the reach of the human operations team and the ground science team. Building on that, we're in the process of deploying an onboard planner, which is AI software that allows the rover to make certain decisions on the exact timing of activities. And this comes from a study led by Dan Gaines in 2016 that showed that when we do time-based commanding, we have to conservatively time things because, when we do a drive, we need it to be over before we start the drive after the sensing, remote sensing or robotic activities after that. And so because we have to pick times to execute activities, we can't say do it after this. We actually end up padding things, and this shows that we ended up padding on average 28% all these activities. And what that means is when things go better than expected or as we expect, then we spend some time sitting around, and that's not a productive use of the rover. So the onboard planner is AI technology that allows the rover to understand the activities that are executing, and this is showing a plan and execution, and it enables the rover to adjust the plan. So if activities finish early, it can bring other activities forward, or it can take a nap, or if activities run late, it knows whether or not it needs to cut them off, or they can run a little bit long and we'll just start the next activities later. And so this is very important to best utilize these very critical assets that we have at Mars. We also have a helicopter at Mars. The Ingenuity helicopter is the first helicopter to fly on another planet. Ingenuity has now completed over 60 flights on Mars. You can see it at the right there, taking off. And this is the rover is this helicopter is quite amazing. It is able to track where it's going and figure out how far it's traveled and how fast it's traveled, doing motion estimation. And this helicopter is just the first step. There are plans underway to try and develop this concept for what's called a Mars Science Helicopter, which would allow the helicopter to go much further, to choose specific targets for science and approach them and take science images and understand better where it's safe for it to land. And this would enable all kinds of amazing science at Mars in the future. But really what I'd like to give you a highlight of is how NASA's search really relies on advanced AI, NASA's search for extraterrestrial life. And what exactly do we mean by that? So I'm going to talk about two targets, which are some of the most plausible places most likely places that we might find life in our solar system. And the first is Enceladus. Enceladus is an icy moon of the Saturn planet, which is in the outer solar system. And recent James Webb Space Telescope measurements have detected carbon in plumes that are coming from Enceladus, and we're very interested in these plumes because we really want to access this under ice cap ocean at Enceladus, and these crevasses and plumes give us access to some of the material that would be there from the subsurface ocean, rather than having to go all the way down to the subsurface ocean. The challenge is, how do we get down these crevasses and sample these plumes in order to discover, is there life there? Well, a bunch of incredible engineers at JPL, led by Hiro Ono, are leading a project called the Exobiology Extant Life Surveyor, or the EELS, Enceladus Exploration and Mission Concept. And this is a snake-like robot that would be able to go down these crevasses and maintain a stable position by spanning the crevasses and kind of worming its way and drilling its way down to sample these plumes, yet not be knocked into outer space by the plumes themselves. The EELS robot is quite large. It's about 4.5 meters long and weighs about 100 kilograms, or over 200 pounds. It has many of these segments, and hence it has 30 degrees of freedom, and depending on which configuration, it has 10 to 20 screws that allow it to move along different kinds of terrain. It has an inertial measurement unit, it has a LiDAR, it has cameras, it has pressure and temperature sensors and force torque sensors that allow it to understand the shape that it's taking and to figure out what's the best shape to explore. And this AI software, or autonomy software, has to manage a lot of different things. It has to take the mission goals and decompose that into task and motion planning. When it has to move, it has to figure out the path it wants to take, and it has to take that path by doing shape and screw control, as we're going to see. And then at the lower level, the shape and screw control is configured by actuator control. While it's doing this, it has to manage three concurrent processes. One is the risk. What is the risk? Because the most important thing is that you can't lose the EELS robot, or that's the end of your mission. And then it has to balance exteroreception and proprioception. Exteroception is sensing of the world outside of the robot itself. Proprioception is sensing of the configuration of the robot, including the forces on the robot that allow you to figure out how to move the robot. And so it has to balance all of these factors using artificial intelligence in order to explore correctly, to balance the rewards of finding different sample locations against the risk of falling down the crevasse or being blown out from the crevasse. And so what it just fundamentally is the balancing of moving and scanning. So moving is actually progressing towards your goal and getting places so that you can sample. And the scanning is taking more data so that you can figure out where you want to move and if it's safe to move. And so we motion plan, and then we introduce scanning when risk, in order to reduce the risk in the threshold of the plan. And this is all based on what you see in the map. And we have two different approaches. One is a partially observed Markov decision process, which produces stochastic action choices that are suboptimal. And then we have the more deliberative approach, which is this mixed integer linear programming approach, which finds an optimal solution, but it has a challenging covariance growth model. And so the EELS robot uses these two approaches complementarily to achieve this two-stage motion planning. So, for example, if the robot starts out in the upper left, if there's low uncertainty, it's going to basically be moving very rapidly. As it gets further along, maybe it's worried about this gap to the left, and the uncertainty bounds are starting to worry that it's going to fall into that void. In which case, it's going to start scanning more until it goes past that process, that sort of more risky area, and then it's going to start moving more rapidly and scanning less. So this is actually showing the robot, the one at the far left. The ones at the left are sped up. The ones at the right are more in real time. And as you can see, this robot is very agile, and it actually has a very interesting challenge in order to do both its path plan and its sensing. So this is the snake robot that's balancing risk against reward and figuring out how to explore a future mission to Enceladus. So another target that is quite exciting for us is Europa, which is one of the moons of Jupiter. And the first stage of such a mission, so we already have the Europa Clipper mission, which is going to fly by the Europa moon of Jupiter around 2030. But the next step would be to deploy a lander. And this lander is an incredibly challenging mission because the lander would land with a limited amount of energy from batteries and a very radiation hostile environment, so that it would only survive about 30 days. So based on that, it has a very limited lifetime. Over half of every 3.5 days, you can't communicate to this lander because Jupiter's radiation causes a radio blackout when Europa is behind Jupiter. There's also an unprecedented amount of uncertainty. We don't know what the substances and the clumping and all the physical properties are going to be when we land. It's very challenging even to land in a stable state. And in fact, when we land, we need to trench out these areas, hopefully 10 centimeters deep, and then sample from them and hope to find astrobiology samples that are indicative of either life or precursors to life. And so the whole goal is you land and you have these 30 days and boom, 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 you need to be sampling as quickly as possible. You need to be sampling even when ground cannot communicating with you, because your mission is going to end very rapidly. So we've used a decision theoretic approach to utility and probability. Utility measures how good each of the sampling sites are and weighs that against the cost of sampling them in terms of energy, and then we adjust if the sampling is going better or worse than we expect. And in fact, we even consider how much data to bring back based on how exciting the samples are. If they're negative astrobiology results, we are probably not going to bring as much data back, but if we find a positive signature, we're going to sample again to confirm it, and we're going to send down as much possible data on those sites. And this is very important because a significant portion, as much as a quarter or a third of the mission energy, is going to be spent bringing data back. But beyond Europa lander, there's even, just like on Enceladus, there's these vast oceans underneath the ice cap in Europa that in fact that are believed to hold more water than there is on Earth. So there's an even more mission, a moving more aggressive mission. So you have Clipper, which will fly by, then you have the lander, which will land, then there's a concept beyond that, which is called Europa Submersible, where you land and you melt through this ice cap and you deploy a submersible submarine, an autonomous submarine, to go hunt for life in the ocean itself. So first you have to get all the way to Jupiter, then you have to land, then you have to melt through this tens of kilometers thick of ice, which might take a year or more, and then you have a submersible that has to be completely autonomous. So it might go and take 30-day expeditions away from the base station and come back and hunt for hydrothermal vents, which are these volcanic vents on Earth where they found life in the absence of sunlight in extremophiles, and we want to hunt for those same environments on Europa's subsurface ocean, and like I said, it's for 30 days at a time, the submersible would be entirely on its own. So that's completely artificial intelligence. And this isn't science fiction. We had an expedition in 2016 to the Gakko Ridge, and we just had another one this last summer, northern summer, to the Gakko Ridge again, which is the only known hydrothermal vent underneath ice on Earth. And this was an expedition PS-137 on the Polar Stern, which is a German icebreaker from the Alfred Wegener Institute, and also using a robot from the Woods Hole Oceanographic Institute called NUI for Nereid Under Ice. And we're studying how to best explore find these hydrothermal vent fields and explore them, because that's exactly what the AI would need to do in this Europa submersible mission. And then even beyond that, the unbelievable ultimate challenge is an interstellar mission. So the nearest star to the Earth is Proxima Centauri. It's about 4.5 light years away. The TRAPPIST system is about 10 light years away, which has many Earth-like planets, and so it's even more exciting. The problem is, to get to one of these planets is going to take 50, maybe 70 years if you're lucky. And then once you get there, that's mission has to be executed completely on your own. You can't send a radio signal back to Earth asking for help. If you did, it would take 5 to 10 years to get back here, and then a response message would take another 5 to 10 years. That's 10 years to 20 years lost on your mission trying to close that loop. So the AI is pretty much going to execute the mission and tell you what it found, transmit it all back. And so that's the ultimate challenge for artificial intelligence in the hunt for life beyond Earth. So with that, I'll leave you with the JPL mantra, which is "Dare Mighty Things," and I'm happy to take questions. Thank you for your attention.
Thank you so much, Steve.